This is going to be a redo of example 8-5. So obviously we're going to get the same result, but this time we're going to use the p-value method. So the way that we get the same result is going to be slightly different. These two methods are equivalent to one another, so whatever decision you make using the traditional method, you're going to arrive at the same decision if you use the p-value method. And we'll illustrate the 5 steps going through the p-value method shortly. Let's look at the problem. Example 8-5 on the cost of rehabilitation. The Medical Rehabilitation Education Foundation reports that the average cost of rehabilitation for stroke victims is $24,672. To see if the average cost of rehabilitation is different at a particular hospital, a researcher selects a random sample of 35 stroke victims at the hospital and finds the average cost of their rehabilitation is $26,343. The standard deviation of the population is $3,251, and then at alpha equals 0.01, can it be concluded that the average cost of stroke rehabilitation at this particular hospital is different from $24,672? Okay, so the problem, like we said, is the exact same one that we did last time. So all of the same information is still true. Mu is the hypothesized value for the population mean. That is $24,672. Chi bar, that was the average for the sample at this particular hospital that they computed. That was $26,343. The sample size, N, was 35. The level of significance for the test is still 0.01. And then finally, they're assuming that we know the population standard deviation, and it is 3,251. So the only detail that is going to be different here is just basically the method by which we perform the hypothesis test. The steps are very similar. Step 1 is the same. We're going to state the hypotheses. And so the null hypothesis is there's no difference between this hospital and every other hospital, right? The null hypothesis is essentially always a statement of the status quo, right? If we don't notice any research that points to the contrary, we're just going to assume that things are as they are now. So that's why in the null hypothesis, we're always going to be saying the population parameter is equal to some value. And then the alternative hypothesis, in this case, we're just going to test to see whether it's different from that value. So notice we're not gonna be looking at chi bar here. Don't do that. All right? We're still looking at this same value for mu, but here we're saying that it's equal, and over here we're going to be saying that it is not equal to 24,672. Right? That's the only difference. So in H subscript 0, we're going to say equal sign, and in H subscript 1, we're going to either say not equals, or we're going to say less than, or we're going to say greater than. We're going to say some inequality there. All right. So the next step in the p-value method is to actually just go ahead and compute the test value. So that computation is done exactly the same way. All right, we're going to take chi bar, whatever that was, minus mu. That is always what we are given, or always what we have in H subscript 0. This is sigma divided by the square root of n. Okay. And so we're just going to be substituting in everything that we have here. So we got 26,343 for our sample average, 24,672 for the population mean, 3,251 for sigma, and then for this, we're taking the square root of 35. So that value, let me just look back in my notes at the previous one, and we get z equals 3.04. All right, so there's our test value, and that was one of our steps from the traditional method. I believe that was step 3. We're finding the test value. Okay, so that's another detail that's the same. We just change up the order a slight bit. Now in step 3, we're going to go ahead and compute the p-value, and we can just go ahead and compute this directly, but I want to give you an idea of what that p-value represents. Okay. The p-value for a two-tailed test here, this is still a two-tailed test even though we're not using the traditional method and we're not sketching the critical region itself ahead of time. We're still going to draw this distribution curve, right? That's our same normal distribution curve that we're looking at. We have this z value, that's our test statistic, 3.04, our z value. And in the standard normal table, we can go ahead and use that, right? We have to do a little bit extra work to find the area underneath the curve to the right of this positive z value. All right, so basically, we just kind of use common sense. If 0 is in the middle and we have a positive value, it wouldn't really make sense to look at this area to the left, would it? No, not really. So let's take that away. Okay. And then the only thing here, so we're going to look up this area right here. All right. And let's pause and do that really quickly. Okay, so negative, 3.04, that's going to give us a very high value, and then we'll subtract that away from 1, and we'll get a very low value for that area underneath that curve. So by the way, I'm just doing the trick of looking up the opposite of that value and using the small value for the area. So here, the area underneath this curve is 0.0012. Okay, for a single-tailed test, whether it's a right-tailed test or a left-tailed test, that would be the p-value itself. Since this is a two-tailed test, we're going to take this value, this area, and multiply it by 2. That's the only extra little thing we have to do for the p-value. We have that it is a two-tailed test. So that's where the 2 comes from. And we'll plug in this 0.0012. So our p-value works out as 0.0024. Okay, and now, how do we interpret this result in order to make the decision? Scroll up a little bit. Step 4 is we're going to be making the decision. And how do we make our decision? So our p-value is 0.0024. We're going to look at how this compares to alpha. And that was 0.0, what was it? Oh, 0.0 1. Okay? So, what is the relationship between this? It might help us if we just go ahead and write in some extra placeholder zeros so that these have the same number of digits after the decimal point. So then we're looking at 24 versus 100. We can clearly see that alpha is bigger. All right? And so here, anytime our p-value is less than or equal to alpha, then we will reject the null hypothesis. And so what does that mean for us? We'll summarize the results. And again, whether we reject H subscript 0 or we fail to reject H subscript 0, we're always going to talk about the results of our test in terms of what evidence we found and what the evidence tells us as a result of doing this statistical test. So here we would say there is enough evidence to show there is a significant difference between the rehab cost at this hospital and the national average of $24,672. So that's how we would conclude that. Notice we get the same decision, the same summary of the results, just steps 1, 2, and 3. Really, steps 2 and 3 were kind of just switched around a little bit. So, and then the way that we made our decision was based on a different sort of factor. There is an obvious relation between the p-value and alpha and the traditional method versus the p-value method, and maybe I'll explore that relationship or that comparison, that contrast, in another example in just a moment. But we'll stop now.